In this video, we're going to go through utilizing the angular overlap method to determine the d-orbital splitting diagram that we can expect to find for this complex right here, the pentacarbonyl iron 0 species. And so if we use the angular overlap method, the first thing we'll want to do is we'll want to assign a position to each one of the ligands bound to the iron. And so when we do that, we'll see that this carbonyl will label as 1, this one is 2, correction, not 3, this right here should be 6, and then we'll have 7 and 8. And so these will be the positions that we're going to be using from the chart that we were handed out in class. And so we can see right here all of these different values, and so if we then start filling in our chart to start determining what the energies are of our different systems, we'll start off with the dz squared, and we'll see what contributions we're going to get from the E sigma components of the orbital energies in the system. And so for position 1, we'll get a value of 1. In this case, for position 2, we'll get a quarter. For position 6, we'll get 1. For position 7, we'll get a quarter. And for position 8, we'll get a quarter. And so these quarter contributions come from the so-called donut around the dz squared. That's where those sigma contributions come from. And so next, we're going to look at the pi contributions. And for dz squared, in this geometry right here, there's going to be 0 pi contributions in each case. And so the total energy for dz squared is going to be equal to 2.75 E sigma. So next we will look at the dx squared minus y squared. And so in this case, for positions 1 and 6, we will have 0 contributions to the sigma component of the energy. For position 2, we will get 3/4. And then for position 7 and 8, both of those will provide us with 3/16 of a full E sigma. And then we can then add all of that up, and so we'll get then as our sigma contribution a contribution of 1.125 E sigma. So if we then now look at the E pi contributions for positions 1, 2, and 6, we will get values of 0. But for positions 7 and 8, because these are off axis, they will be able to form pi contributions, pi bonds with the dx squared minus y squared, and the amount of that contribution is going to be now a value of -3/4 for both the carbonyls at position 7 and 8. And so the reason that I'm labeling these as negative is because COs are pi acceptor ligands, meaning that they will stabilize any pi contributions that happen in this case. So these orbitals are actually going to be the bonding orbitals, whereas in the cases of the sigma bonds, those will all be the anti-bonding orbitals in these cases. And so those will be going up in energy. And so if we add up now our E pi contributions in this case right here, what we'll get is a pi contribution of -1.5 E pi. And so the next orbital that we'll look at is the DXC. And so the DXC has a 0 sigma contribution for each ligand. And so we will get zeros all across there. For the E pi, in the case of position 1, we will have a -1 value. For position 2, -1, position 6, -1, and then in position 7 and 8, there will be very minimal overlap, and so what we'll get is a -1.4 in both of those cases right there. And so in the case of the DXC, the energy change that's going to happen here is going to be a value of -3.5 E pi. So if we look at the DYZ, what we can now see is that just like the DXC, it will have 0 contributions from any sigma bonds. In the case of the pi bonds, what we will have is a value of -1 for the 1 position. For the position 2, we will have a value of 0. For position 6, we will have a -1. And then for positions 7 and 8, we will have overlaps that will provide us with a stabilization of -3/4 E pi in those cases. So if we add all of these up, we'll have -1, -1, negative 3/4, negative 3/4, what we get is negative 3.5 e pi. So the next and final orbital that we're going to look at is going to be the dxy, and so the dxy is going to have 0 sigma contributions from positions 1, 2, and 6, but in the cases of position 7 and 8, we will have sigma bonds that are going to form, and then each of those is going to provide us with an energy difference of 9/16 e sigma. And so we will, if we add those up, we will get a value of 1.125 e sigma. And then if we look at the e pi, we'll get for position 1 a value of 0, for position 2 a value of -1, for position 6 a value of 0, and then for positions 7 and 8, those contributions will be negative 1/4. And so adding all of that up, what we will get is a value of negative 1.5 e pi. And so what we can see right here is the total energy in each case. And so in the case of the dz squared, we will have an energy increase of 2.75 e sigma. In the case of dx squared minus y squared, we will have an energy change of 1.125 e sigma minus 1.5 e pi. We will have, for xz and yz, that energy difference is going to be negative 3.5 e pi, and dxy is going to be just like dx squared minus y squared, where we'll have an energy change of 1.125 e sigma minus 1.5 e pi. And so if we draw the MO diagram for this species, which I'll do in a second after cleaning up this board, we'll be able to see the energy differences that we can expect in each case. Now that our board is cleaned up, what we can do is we can draw the d-orbital splitting diagram. And so if we just consider this position right here to be the initial energy of all 5 d orbitals, the first orbital that we can draw is going to be the dz squared. And so we will draw that one all the way up top here. And so we can see that that energy difference in this case right here is going to be a value of 2.75 e sigma. The next orbital set that we can then draw is going to be the dx squared minus y squared and the dxy. Both of these will have the same change in energy of 1.125 e sigma minus 1.5 e pi. And so I'm going to draw these orbitals to be above the initial energy rather than below it, even though the coefficient before the e pi is greater than the coefficient before the e sigma. E sigma energies are on a range from 2 to 9 times greater than e pi. And so even if this was a situation where e pi was only 2 times greater than, if e sigma was only 2 times greater than e pi, we would still have a much greater contribution from the sigma in the energy change than the e pi. And so what we're going to do is we're just going to draw these two to be above. And so one of these is the x squared minus y squared, and the other one is the xy. And so this energy change right here is going to be 1.125 e sigma minus 1.5 e pi. And so finally, we can see right here that the dxz and the dyz are both going to go down in energy of 3.5 e pi, and so we can draw those down here. And they're going to go down by 3.5 e pi, and so we'll have the xz and the yz right here. And so as a check for ourselves, we can also make sure that all of these orbitals have the right degeneracy that we would expect in this case. And so if we look at the molecule, we can see that the molecule has D3H symmetry. Looking at the character table, we'll see that the dz squared is going to have the character of A1 prime. In the case of the dx squared minus y squared and the dxy, they're both going to be degenerate since they are in the enclosed parentheses, and they will have the symmetry of E prime. And then similarly, the xz and the yz will have to be degenerate with one another, and they will have the symmetry of E double prime. And so we can see right here, based on our point group analysis, our MO analysis from right here, we can see that this does line up as expected, where we have our dz squared on its own, the x squared minus y squared and the xy degenerate, the xz and the yz degenerate. And so the next step in this case right here would be to start filling in the MO diagram with the number of electrons. And so we can do that by looking at the metal that we have. So we can see that we have iron. Iron on its own is iron 0 is D8. The oxidation state is iron 0. And so that means we're going to have 8 electrons. And so if we fill these in, what we will get is a completely filled E double prime and E prime set of orbitals with the A1 prime as the LUMO in our species. And so if we were to do any magnetic measurements on this, we would expect to get a mu effective equal to 0 or very close to 0, since we should not have any unpaired electrons.